In this video, we're going to talk about the common oxidation states for transition metals and some of the effects that has. Here from our book, we can see this nice table that shows us the obtainable oxidation states and even the common oxidation states for the 3D transition metals. Scandium, titanium, vanadium, chromium, and so on, well, they can all have no oxidation. You can have the pure metal. Some of these are rather difficult to obtain that way. It can take some work to isolate it, but all of these are metals that we can obtain. However, once you want to start losing electrons, not every form of it is stable. If we look over here, zinc can become zinc 2+. However, it cannot become zinc 1+. Many researchers have attempted to make a zinc 1+ compound, and to date, none have been reported in the literature. However, that is completely possible to do for several of the other transition metals. So what's going on a little bit here? We got to remember what electrons you are losing. Remember that you lose your s electrons before your d. Because zinc has a full set of 10d electrons, if we have our 4s and our 3d, normally we think that our 3d are above a 4s. And in a neutral element, this is the case. But as you start ionizing, your orbitals contract, and they do so at a different rate. Net result is once you're an ion, our 3Ds end up below our 4s. As a result, it is actually the 4s electrons that get lost first. Destabilizing zinc by removing just a 4s while having a fully filled 3D with all 10 electrons in it is not as stable as simply removing both 4s electrons and becoming zinc 2+ with an unoccupied 4s and a fully occupied 3D. As a result, stabilizing that 4s with one electron in it isn't something that is so far achievable. Stabilizing a situation where zinc has lost both 4s electrons but not any more of the 3D is actually very common. Removing any more electrons from the 3D is both energetically hard, due to already being a 2+ ion, and would involve creating instability as you would unpair and make the orbitals no longer equally occupied. Unequal occupation of degenerate orbitals that are the same energy, results in instability and is higher in energy. As a result, it's just not something that's been observed. Other elements, on the other hand, can have quite a number of oxidation states. Vanadium, which would be 4s2 3d3 in its neutral form, has 5 electrons that it can lose from its 4s and 3d. You'll notice its d electrons, there are 3 when it's neutral, there's still 3 when it goes +1, there's still 3 when it goes +2. It's losing those 4 electrons first, then it starts to lose the 3d electrons. This is a trend you can observe throughout this diagram. Those 4s electrons are lost before the 3d electrons are. Since vanadium has multiple unpaired electrons in the d orbital, removing one doesn't involve any instability. As a result, this means that manganese, with 7 electrons between its 4s and 3d, actually has the capacity to become the most oxidized of all of the transition metals in our 3D series. It can go all the way down to losing all 7. The 4s electrons can be unpaired and removed, and the 3D electrons are not paired and can be removed without introducing too much instability. Permanganate Mno4 with a minus is one of the more reactive oxidating materials that we have. It's this deep purple and is used in a lot of reactions. It commonly will become manganese 4+ or 2+, depending on the reaction that happens, where it is reduced by oxidizing some other material. So while there are a number of oxidation states and reasons why we can obtain very high oxidation for the center of the transition metals, but we get much lower oxidation states for either the start or the end of the transition metals in a series. This also leads to some of the intense properties of transition metals, such as color. D orbitals we draw as a line, and on a free atom or free ion, this would be the case. They'd be equivalent. As we'll see in later videos, complexes, where various molecules attach to your ion, waters, chlorides, and other things, actually result in the d orbitals no longer being perfectly aligned. Well, we'll dive into that more. The brief version of it is those d orbitals get spread out. As other things overlap them, it changes the energy level of those d orbitals. They can go up or down. They can split, some of them equally up and down, some spread out more. This creates a difference in the various d orbital energies. So as the other molecules stick to iron or copper or whatever transition metal you're looking at, the net effect is that it splits the d orbitals into one of these patterns. Well, the energy difference between these tends to fall in the visible light range. If you push them a little farther, if you get them more distant from each other, you'll end up in the ultraviolet. But especially things like octahedral compounds, tetrahedral compounds, and the like, the differences between those d orbitals is in the visible light range, which means if you have some electrons in one, a light can be absorbed, exciting those electrons up. Well, remember when light comes in from various colors, if one of them's absorbed, the light that passes out is missing that color. Absorb your green, you'll end up with red and blue and look fairly purple. Absorb your red, you'll end up with green and blue and look pretty intensely blue usually. Absorb your blue and you'll end up with red and green and look sort of yellowy orange depending on exactly what wavelengths are being absorbed. Organic molecules tend to always look white, and so they either pass through clear or refract off of it and you get white light. Transition metal compounds, however, often have intense colors. These can vary greatly, but they are a big part of why minerals like rubies and sapphires and the like have their incredible colors. It is impurities of transition metals that actually makes those. Which type of shape can be done, which electrons are available to excite, which ones aren't, all that can be affected by the oxidation state. So I introduce it here. We'll dive more into it in our later videos.